Okay, let's get started here on our very last live lecture. Going to be just reviewing for our final exam, which is a week from today. So next Tuesday, and your choice, whether 8:30 in the morning or 6:30 p.m. You don't need to let me know, just show up. Okay. And as always, like you did for exam one, exam two, you'll go to the Moodle website and get your exam there. In fact, so week from today, you'll go into the Moodle website. I'll make it available up there. But you know the drill. Okay, so let me get back over here. Now, but in the learning module, so learning module 27, the last one, because you know how it's always been. Whenever the learning module's been right before an exam, it's always had great study guides in it. And module 27 is no exception. So if you go into the activities, I've got a nice long list of practice final questions. Now, don't worry, your final is not going to be that long. It's just a long list to give you lots of practice. And of course, these are the highly detailed solutions. Let's see here. And of course, remember, review your exam one and your exam two. Let's see. Oh, and for the concept questions, see, do I actually say that here? But I limited to the ones after exam one, because a lot of what we're still doing to this day includes the ones that were after exam one. So let's see. Yeah. Oh, there we go. There's where I tell it. So concept questions 17 through 48 are the ones I'll be selecting from. I know it was there somewhere. All right, so let's just set this aside. Get that out of the way. Get that out of the way. And here's a document. Now, just so you know that these documents we're looking at, I always make them available to you. So if I get back here to the main menu, external links, files from the live lecture. So these are ones from 3, 4, and 5. And of course, I'll have the one for this one. And the link will be there. So just so you know that all these are available, just like from lecture 5, I had these available. Oh yeah, these are the ones when I was showing you how I was going to grade exam number 2 before you took the exam. So that was a really helpful live lecture to be in, and you had the documents right there. Let's see, and then for here, this was back working on chapter 7 and 8, so you might find that very helpful to review if you had any trouble with that on exam 2, and so forth. But let's set this on down. Now, this little document kind of serves two purposes. One is it's a nice way to get a big picture overview of what you've done this term. And it's sort of kind of like a way to gloat over what you can do. But it's a way to review without getting lost in the weeds. You're able to stand back at the big picture. For example, if you need information regarding some measurement for a huge population, well, and you know nothing about that population, the first thing you'd want to know would be, well, what's the typical measurement for that entire population? And of course, that's the population mean you want to know. Well, if somebody made a claim that they know what it is, you can test that claim with a hypothesis test. Or maybe there's no claim involved and you just want to get an estimate of that population mean. You can do that doing a confidence interval. That'll give you an estimate of it. Will it be a good one? It will be if your confidence level is high and your margin of error is small. And if that margin of error isn't small enough and that confidence level isn't high enough, you know what to do about it. Get a larger sample size. And you've got a formula to calculate how big that sample size needs to be. So those same principles apply to binary data. Big, huge population, but this time it's binary data. You can accomplish the same thing. Now let's get into the bread and butter of inferential statistics. And that's where, I got to adjust this so it doesn't jump around on me. There we go. And that is when you're comparing two huge populations with each other, and you want to know, are they the same or are they different? The null always says they're equal to each other, and that would be population means if you're dealing with quantitative data, and population proportions if you're dealing with binary data. So you can do a hypothesis to test the claim, know that they're different, or you're just interested in the magnitude of the difference. And you can do a confidence interval that will give you an estimate of the magnitude of the difference between your two population means or population proportions. Now, here's an interesting one. Now, this is going to take you back to exam number 1. Can I use one quantitative variable to predict another quantitative variable? Because I'd sure like to, because I like to be able to predict the future. Well, you did that back in chapter 4 with linear regression. And so that was the purpose of that, being able to make predictions. Now, let's not forget what you did way back in the beginning. Let's suppose you got all the data for this population of interest. What can you do? Well, you organize and summarize it, which is what's known as descriptive statistics. And technology makes that pretty easy. And you did that in the StatCrunch assignment. You let the Minitab software package, no, excuse me, not Minitab, you use StatCrunch. And so StatCrunch organized and summarized that, and by golly, you were able to interpret what that tells you. You know, the shape tells you a story. The middle or center tells you the typical data value. The spread tells you how much variability there is in it. So that's a nice, quick, short summary, big picture of your fundamental skills that you acquired. And the idea is that if you've been practicing, and I'm sure you have, those few questions you ask yourself and you know exactly which statistical method to use, then you'll know exactly when and where you can apply these. And you know how to check conditions, so you know it's appropriate to apply those. And then, of course, finishing the job, actually carrying it out. Now, for those of you who have been doing a great job, you say, oh, does the fun come to an end now? Not necessarily. There can be more because you're just getting started. You've got some nice tools on your statistical tool belt, but there's more to be had. And so now, of course, this is automatically going to happen for some majors, because if you're a business major, you're going on to business statistics, the old BA 282. And this class prepares you for that. You know, it's going to keep reusing the same concepts that we learned here. Now, you psychology majors, you're going to Psych 225, and this class prepares you for that. And in that class, you're just going to keep reusing these same concepts. So the better you mastered this material, the easier that second term is going to be. Now, you biology majors, math majors, you'll be seeing me next spring term with Math 244. We offer it each spring term, and I do offer the option that you can do it online using my Stat Lab. So your access code that you have right now, that's good for this spring term. You won't have to buy another access code. You'll be able to hop right in there. All right. So this document, I'm not going to spend much time on it, but it shows you the other statistical methods you'll be able to do. Because you know how to compare two population means, but what if you had 3 or more? Could you compare them all at the same time? Yes, you can. And same with population proportions. And I'll just leave the rest of this for those who are curious to see the other things that you can do. But you'll know, but the thing when you look at all these, I want you to notice what they all have in common. And every one of them, the null hypothesis can be identified as being nothing unusual is happening, no difference, no association, no correlation, no nothing. And the alternative is the opposite of all of those. And of course, the significance level is always how small your p-value has to be, because in all these hypothesis tests, you get a p-value. And I do hope by now you know how to use that p-value to come to your conclusion. All right, so you might find that document helpful. Now, last time when I was going over hypothesis tests, this was the little template, for those who are getting started. But the idea is that should have used this enough that you have weaned yourself away from it, that you can remember. Well, first of all, good to remember these questions you ask yourself. That's why I encourage you to use this. Now, was I asked to test a claim? Because I wouldn't use this unless I was asked to test a claim. What type of data is it? You always got to ask yourself that. Are the conditions met? Always check that. And then always show and state your hypotheses, significance levels given to you. You should always write down what TI function you're using. For partial credit, in case things go awry, this tells me you knew the correct statistical method, so I can give you credit for that. I showed you last time how to use this to make a little sketch, very simple, easy one to make, but it's incredibly helpful for students working on learning the logic behind hypothesis tests. This gives your brain a framework, a picture to better grasp the concepts. It's much harder for your brain to grasp these concepts without this sketch. So put things in your favor and use it like I showed you in the last live lecture. And you'll state your conclusion. And notice what we often do, in fact, we should always do after a hypothesis test, is follow up with a confidence interval. It always gives you more helpful, insightful information that the hypothesis test can't give you. First of all, and plus confidence interval lets you know if your sample size is large enough to get things narrowed down. Because that interval is really wide, well, you're not happy about that. So you calculate how much bigger the sample size would need to be. But this gives you an idea how all these things fit together. Hypothesis test followed by a confidence interval followed by a sample size calculation. All right, so let's set that aside. Oh, now here's a very helpful thing for you to keep reviewing is the hypothesis test summary. Now, of course, you probably have already seen this because you've got your little Math 243 tutorial. And if I open that up, you've learned that when I go to these lecture notes, there's always these study guides. Like that's a study guide for exam 1, study guide for exam 2. And I'll bet this is a study guide for the final. So here's that hypothesis test summary I was just looking at. We also got some other flow charts and some poster board documents that you might find very helpful to help you review. In fact, let's take a look at this one. Hey, you notice right off the bat, it's got the hypothesis test summary. What else does it have? Well, you might find that helpful, letting you know about type 1, type 2 errors with hypothesis tests. There's that little flow chart so you know which sample size calculation to use. This is when you're working with one sample and you know which one to use or when the conditions are not met. Same thing with confidence intervals. This is what helps you keep straight whether you're working with the quantitative data or the binary data. They help you keeping the two worlds separated so you didn't get these two confused with each other's. Because that was real important because as you start checking conditions for the statistical methods, the rules that apply in this world don't apply over here. You had to keep them separated. And this helps you remember a little something about the sampling distribution for the sample mean. Same thing here. Oh, and there's chapter 4 summary. That might be worth reviewing because it's been a while since you looked at it. That's back on exam 1. And some basic stuff there. And this is just a picture of how you could post it on one board if you want, or you can just kind of tape all these pieces of paper together if you were to print out these pages, or just the ones you want, and pin it up. And whenever you walk by it, take a few minutes just to review all these concepts each day between now and the final for a whole week, just every day reviewing those concepts. So let me get back over here. So, you notice that these are the fundamental concepts that apply to all hypothesis tests. Now, there's not going to be any z-test or z-interval. We can pretty much cross that one out. I just put it in for completeness sake. But these are the two for when you just are looking at one population. And when you're dealing with two populations, you have these three. So these are the last ones you were working on, the last three homework assignments. But it's kind of helpful to have it all in a one-page summary, keeping straight, what the hypotheses look like. Notice how unique. You can just look at the hypotheses and that tells you what statistical method is. All right, let's see here. Oh, I didn't want to get that. Let's see here. Am I out of sync? So we did that. We got that. We got this. I must have deleted though. Okay, better get it back in here. Hold on. Because what I thought would be helpful is we could take a look and get some practice with identifying which statistical method to use. So let's go here. And that was identifying the statistical method. There we go. This is what we want to look at. So the idea here, let's just look at one at a time. We don't want to confuse any issues here. And so let me get my calculator over here. Scoot that over there. And also, we should also get that formula sheet up here. So I will. I think we get everything to show there. I don't think you really need to see too much of the first one there. Anyways, let's see if we got enough showing here. Oops, I don't want to be showing that one. Gosh darn, I keep doing that. There we go. Oh, I should bring it next to it. Yes, I did. There we go. All right, so for this first one, a random sample of 2,000 non-fatal auto accidents showed that 752 of them involved the use of a cell phone. Now, for A, they say, now find a 90% confidence interval for the proportion of all non-fatal auto accidents involve the use of a cell phone. So identify, what statistical method is that? In other words, do I need to go to something on this formula sheet, or do I go to a function on this calculator for that? Just identify what it is you need to solve for. And for B, how large of a sample would you need in order to be 99% confident and have a margin of error of 1.5%? So once again, we're not solving this, just saying what you're going to use. Okay, so here's the questions you run through your head. Number one, what are they asking for? Hopefully you can say that, oh, confidence interval. It's a confidence interval problem. All right. Now, next question is always, what type of data is it? Well, I'm going through this sample of 2,000, and from each observational unit or individual, I'm not measuring anything on them or from them, but I'm categorizing them. I'm putting them into this category involved in the use auto accident that involve the use of a cell phone. Either they are in that category or they aren't. So it's binary data. So and the third question is, now how many samples are taken? One or two samples? Just one random sample. All right, so this is a one sample confidence interval. So let's go past all these hypothesis tests and look at our confidence intervals. Which one is it? Okay, well, it's just one sample, so throw all the ones with the two out they go. And it's binary data, so throw out Z interval, T interval. Those are for quantitative. Well, you only got one left. So that you could deduce that this requires the use of one prop Z. All right. So, and that's as far as I'm going to take this for now. Because if you, once you get to that point, you really should have no problem. Really, you go in there and you're prompted for what to put in. So by now you should know what these symbols mean, for gosh sakes. And you just put them in, hit calculate, you get that interval and put it into words that anyone can understand. Like you did on exam number 2. So let's go jump to B. Now, how large of a sample would you need? Okay, what are they asking for? These words tell you. It's a sample size calculation. So it's one of these 3 formulas here. Well, which one is it? Well, our next question is, what type of data are we working with? Well, we already figured that out. It's binary data. Okay, it's binary data. We can cross this one out because see, that has the standard deviation in it, telling us that's the only one for quantitative data. So it's between these 2. Now, decide between these 2 is, do you have a p hat? Now, if you're just looking right here, say, I don't see a p hat. Is this a follow-up question? It is. So up at the very beginning, oh, I do have a p hat. The 752 is the x, 2000 is the n, and my p hat is x divided by n. I got a p hat. All right, so if you got a p hat, which formula is it? The one with the p hat. All right, so you'll take for a p hat, that'll be 752 divided by 2000. E, the margin of error, is 1.5%, and 1.5 is written as a percent. So how do you turn that into decimal? Divided by 100. So 0.015. So that's what I'm going to put in for my margin of error E. And of course, I'll get this critical value just right from this little table. Since they want 99% confidence, I'm going to put 2.5758 in for Z, that critical value. Then all you got to do is calculate it. So once you know the formula or the calculator function, the rest is probably pretty easy. So we've got, that's what I want to focus on right now. Are you good at that? On every exercise you do, practice, always practice asking yourself those questions. Saying, now how would I be able to identify this on the final exam when these things are all jumbled together and I don't know what's coming next? And that's what that long list of practice final questions is going to give you practice with. So let's take a look at number 2. So I got 50 randomly selected people with colds, and they're given dozanol. And 60 randomly selected people with colds are not given dozanol. So the blood pressure is measured for each person, and here's the statistics from these 2 groups. So probably what's really going on here, this sounds like a clinical trial. And maybe what they actually did was they had willing participants and who have colds, and they randomly assigned them to the 2 groups. So we can treat it like 2 random samples. And these 2 groups, because they were randomly assigned to 2 groups, they're actually going to be quite similar. Their differences are going to average out thanks to the magic of randomization. And the only difference is that one group is given dozanol and this one is not. It's known as the control group. So the only difference between them is whether they got the treatment or they didn't, but they think they did. So we got to test the claim that dozanol affects blood pressure, either increases or decreases it. So we want to know if there's a difference in blood pressure between these 2 groups. So what are we going to use to solve that? And then we're going to follow up, I guess, with a confidence interval for the difference between these 2 population means. So let's go over here. I've got here with the hypothesis test. So which hypothesis test is it? Wait, how'd you know it's hypothesis test? He says, right here, Larry, it says test the claim. That's what a hypothesis test is. All right, you're correct. It is a hypothesis test. So second question, what type of data is this? Well, we're measuring blood pressure. That's quantitative data. All right. Third question. How many samples were taken? One or two? Well, let me count. One, two. All right. So it's a two-sample hypothesis test for quantitative data. Which one of these hypothesis tests is it? Well, it's two samples, so it's going to have a two in it. So all the ones that don't have a two, throw those three out. See that 2 prop Z test? That's for binary data. Throw that one out. Well, that's between the Z and the T. Throw out the Z because we always use the T when we're using the sample standard deviation. So you are able to deduce, after throwing everything out that it couldn't be, you're left with what it is, the 2-sample T-test. All right, at that point, you go in there and you're just going to be prompted to input all that information like we were doing last week. Whichever inequality is in the alternative hypothesis, pull, just ignore it, leave it on no, highlight, calculate, hit enter. You'll get your p-value and you can use that to state your conclusion like we did last week. Now, if you want to follow up with a confidence interval, well, that's easy. Just replace the word test with int, and that's what you use. And that will give you an estimate on the magnitude of the difference between your two population means. All right, so that's as far as we're going to take this. Our focus is on what functions do we use on our calculator or formulas if need be. Let's take a look at number 3 here. I'll shrink this down a little bit so it doesn't get distracted here. So, let me get back over here. So a fast food outlet claims the mean waiting time in line is less than 1.5 minutes. Oh, you think so, huh? We'll see about that. Maybe you want to test that claim. So you took a random sample of 20 customers. The sample mean was 1.2 minutes with a sample standard deviation of 0.7 minutes. Hey, that was a small sample, less than 30, and this is quantitative data. So our method won't work unless we have a normal population. Well, one statistical method is take that small sample and use it to create a probability plot. And the probability plot shows that the data for your sample was not skewed. And the box plot we use made from that data shows no outliers. Then it's reasonable to believe that the population is normal that we sampled from. Well, in that case, we're all right. Oh, we're okay. Our conditions are met. Now, for a significance level of 5%, test the fast food outlet's claim. So you're testing a claim, that makes it a hypothesis test. So which one of these hypothesis tests is it? Well, let's think now. What's the second question we ask? What type of data is this? It's quantitative data. We're measuring the waiting time. All right, third question. How many samples are taken? 1 or 2? Just 1. All right, 1 sample hypothesis test for the population mean because it's quantitative data. Well, let's see. So we'll throw out the 2s because it's just 1 population. I'm going to throw out 1 prop Z test because that's binary data and this is quantitative. So the only thing left is Z test and T test. Throw out Z test because we're using the sample standard deviation. That's why we use T test. All right, so now that you know that, you'll be able to go in there after you set up your hypotheses like we were working on last time. You'll be able to get that p-value and state your conclusion. Now, it didn't ask for it, but sometimes they'll ask you to follow up with a confidence interval, and you'd use T interval just to replace the word test with interval, and you'll know that, oh yeah, T interval is what I'd follow up with if I were asked to do it. How about number 4? Airline claims that the no-show proportion of all their passengers is more than 10%. So you want to test that claim. So you went and took a random sample of 860 reservations. 114 of them were no-shows. So test the airline's claim using a significance level of 5%. First thing, what are they asking for? Well, we're testing a claim. So that means it's a hypothesis test. All right, so let's go over here. Which one is it? Well, let's see, what type of data was this? This is binary data. We're going through that 860 and we're putting them into one of two categories. Either they were no-shows or not. And how many samples were taken? Just one. One sample hypothesis test for the population proportion. And you'll deduce that's one prop z-test. And if you were asked to follow up with a confidence interval, it'd be one prop z-int. So look at this one. Scroll down a little. Okay, a manager wishes to determine the relationship between the number of miles in hundreds, the sales representatives travel per month, and the amount of sales in thousands per month. The following data was gathered. So what's going on here? We got 1, 2, 3, 4, 5, 6. So we got from a random sample of 6 sales representatives, they got 2 measurements. This X variable, which is the number of miles they travel per month, and Y, which is the amount of their sales per month. So we got 2 quantitative measurements from each of these observational units or individuals. Is there sufficient evidence to support the claim that there's a correlation between the size of houses, monthly rents? Okay, I'm just noticing, let's ignore this one. We did not get into doing hypothesis tests for this. So this A will not be on the exam. Right? But what you will see is this one. Just like you saw on exam 1, find the equation of the least squares regression line for this data. So, and you say, now how did we do that? Well, let's go back, go down memory lane. First you had to do is this, press stat, 1 for edit. Oh yeah, you have to clear your list. Oh, you cleared your list. Hey, why don't we actually do this one? You know, it's been a while since you've done this. So let's do this. Let's put the X data in list 1. Once you get that in there, then go over to list 2, and let's put in the Y data in list 2. And let's double check. Now, these have to stay paired up with each other because these are the 2 measurements that we got from each observational unit or individual from our population of interest. 39. Now, mine look a little familiar, like what you were doing last week. Not last week, 2 weeks ago. Last week, you were doing nothing. Well, maybe you were reviewing. But 2 weeks ago, when you were finding the differences between matched pairs. But here's the huge difference. You're not being asked to test the claim that there's a difference between your matched pairs. What you're doing here is you're just trying to see, can I use this X variable to predict what this Y variable is? So they're very, very different questions you're trying to find out about. So even though, you know, these are paired up with each other and it feels like, hey, this is just like, well, not just like, but you're actually finding out it's quite different. It's just that you haven't looked at this in a while, probably. Okay, well, once you got that in, what we did was we pressed stat, pressed the right arrow for calc, and we did choice number 4 for linear regression. Select that. And if you always put the X data in list 1 and Y data in list 2, you don't have to put it in there. Because in other words, I do not have to do this. Second 1, then a comma, second 2. But if I don't always put my X data in list 1, Y data in list 2, I would have to type this in. But if I leave this blank, it assumes this is what we're doing. I'll hit enter. Now, maybe you've changed your batteries on your calculator or something, and your calculator got reset. If that's the case, then your R squared and R may not be showing up. So let me show you how to get that back. So if you don't have the R squared or R, you just need to get into this catalog here. You get into the catalog by pressing the second key, the 0 key, and you can just press and hold down that down arrow key. So I just keep scrolling on down till we get down to the D's, and you want to get the pointer at diagnostic on. Hit enter to select it and hit enter again. And once you do that, then you'll be able to press stat, press your right arrow for calc. You can go to 4 for linear regression. This time, let's just hit enter. And you see, yeah, I don't have to do that L1, L2. And then what you would do is, in fact, let's just scoot this over here. Let me get my little document camera over here. Let me write out the work just like you would do. See, all right, we need to give the equation. I don't want to just copy down these 3 lines. You want to put it together to show that you can do that. So you have y is equal to, now a is the slope. So I'm going to round to the second decimal place because nothing was said, and so that's what we'll do by default. 5.44 x plus b, and b is the y-intercept, 33.39, but that would actually round to 40. 33.40. So that's the line that best fits the data. Now, I've got an R equal to 0.9727. Now, for R and R squared, one of these can be written as a percentage and the other cannot. This one cannot. Why? Because R can be between -1, +1. That is not a percentage. Percentages are between 0 and 1. So obviously this couldn't possibly be 1. But notice that, you see, the closer R is to 0, the worse the fit. The closer it is to either +1 or -1, the stronger the fit. Is that pretty close to 1? It sure is. So that's a strong, positive, linear correlation. Very, very strong. Let's see, let me move that light over. Oh, let me scoot this over, and then I think maybe the light won't be so bad. There you go, make it easier to see. Now, then we got our R squared. Now, the thing about R squared, that can be written as a percentage because it can only be between 0 and 1, and writing those as percentages, 1 written as percentage is 100%. So my R squared, I'll write it as 94.62%. And let's see, if you remember how to word that. So we can say that 94.62% of the total variation, oops, not tattle, total variation, there's my A, in Y is being predicted by X. Now, just to help you visualize that, I'm going to actually make the scatter plot and the regression line on here. Now, this is not anything you'd be asked to do on the exam, but it helps explain what this means, helps you visually see what this is talking about. So let me press Y equals, and I would put, now normally we keep this all blank, but I'm going to put in my equation here, 5.44, to get the X, that's kitty corner from the second key, and plus 33.40. Now let's press second, Y equals. Oh, if you've got more of one of these plots turned off, we probably, all of us should press 4 and hit enter so the plots are turned off. Now press second, Y equals. Let's select 1 for plot 1, press enter to turn it on, hit the down arrow, and this is the scatter plot. So I'm going to highlight the very first one and hit enter to select it. Now, where's the X list? Well, that's in list 1, so I got to press the second key and 1. Hit enter. Y list is in list 2, so I press the second key and 2 for list 2. Now, just like we did for box plots, what were the next 2 keys we pressed so we'll get a nice viewing window? Zoom and 9 for zoom stat. There you go. So those points look pretty close to the line, don't they? Well, we told you it was a strong positive linear correlation. But what's this total variation in Y business? Okay, so here's your Y-axis. So you can see the very largest Y value is up here, the very lowest is here. So that range of Y values, that's your total variation in Y. Because you see, before you knew about this regression business and you were only looking at those sales, you say, as I go from one sales rep to the other, I never know what as I randomly select them, I never know what their sales is going to be, because it varies so wildly. Some are way up here, some are way down there, and others are in between somewhere. So how would I be able to predict what a sales rep sales are going to be, the sales reps sales going to be? Well, you really can't if you didn't know about regression. But when you dawned on you, hey, this X variable, is that going to explain or help me predict it? How much of this total variability here is going to be predicted or explained by this X variable? Well, if this was 100%, it would be explaining 100% of it, wouldn't it? But then every single point would have to be smack dab on the line. Well, it's not that good, but it's still not that far from it. I mean, look how close we are to 100%. Okay? So I thought I'd spend a little time going over that because it's been a while since you've seen it. But this is the sort of thing you would be doing on the final exam, just like you did on your first exam. Oh, I guess I can move that over here. And we can get, I guess I could put that away for now so we can see the calculator. All right, let's see what else we got. Oh, this is going back, isn't it? So the following data is from a random sample. Here's a histogram of the data. Now, what I would have probably should have done here is told you to make a stem and leaf display, just like you did on exam number 1. So expect that that's what I would do. I'd tell you to make a stem and leaf display. And if you did, it would show you the shape. Okay? And you would see that the shape. So what is that shape? Well, that's a skew there on the right side. So it's right skewed. And there's a gap here. So you suspect we got some outliers. Well, you want to confirm whether you have outliers by making a box plot. And so that's what it's telling you to do here. So tell you what, it's been a long time since you've done this. So why don't we do this? Let's put this data in our calculator. And let's do this. Let's make a stem and leaf display. And do not split the stems. Don't split the stems, make a stem and leaf display, and then make a box plot. All right? So I'm going to go ahead. I'm going to press Stat, 1 for Edit, clear my list. I'm going to enter in my data. And I'm going to give you a little time so maybe you can at least get started on this. So if you got your data in, one thing that will make the stem and leaf a lot easier for you is if you sort the data. Now you don't have to sort it. I'm just telling you it makes it easier. So that's what I'm going to do right now if you want to follow along. So I'm going to press the Stat key. And I'm going to select sort in ascending order. Be sure to do ascending order because when you do a stem and leaf, you always do it in ascending order. So I'll select that. And which list did you put in? I put in list 1, so I press second and 1, right parenthesis, hit enter. Now when I press stat and 1 edit, it's all in order. So I know my first stem is going to be 3. And if I scroll on, I can see what's my biggest stem, 9. So I know my stems are going to go all the way from 3 to 9. So in fact, I'm going to put that over there. I didn't want to cover up the data in case anyone's still entering data. That would be mean. Let me go over here. Let's scoot this over. Okay, so for the stem, let's put these all in because you never ever skip a stem. So 3, 4, 5, 6, 7, 8, 9. So just go ahead and put them all in. That'll make sure you won't do something silly like skip a stem. Because even if there's no leaves, you never leave it out. You put them all in. Otherwise, you can't see if you suspect outliers. I'll put the leaves over here. And if they're all in order, I'll just be going from left to right. So I can see, look at all these in the 30s. 0, 1, 3, 4, 7, 7, 9. So let's just go ahead and put those in. See, this way I'm not hopping all over the place like I would be if it was not sorted. Let's see, so let me go down my list here. Okay, so that was the last. Right now I'll do the 40s. Say 2, 3, 4, 4. So notice how I try to get these to line up nicely because I don't want to distort the shape. 2, 3, 4, 4. Oh, don't forget the 5. Now I'll do the 50s. So let's see, I got a 52, 54, 54. So 2, 4, 4. See how they're lining up nicely? I'm not veering off, distorting the shape. And then there's a 69. There's no 70s. There's no 80s, but there's a 95. So this is helpful information, seeing those blank rows there. Doesn't it look like this lies way out there, far away from the others? So just using my stem and leaf, I suspect that's an outlier, but we want to confirm it. And since I entered my data in here already, well, now I can go ahead and make my box plot. Because you had to make your box plot anyway, so you had to enter the data in. So why not enter the data in and sort it just to make your stem and leaf easy to do? Oh, so let's make a note here. This is right skewed. So notice when I'm trying to determine the shape, I'm not going to, notice I'm doing this before I even get the box plot. I'm not going to trust my box plot to tell me the shape. That's what I use my stem and leaf for. But I'm not going to say that's an outlier. I'm going to have my box plot confirm that. So let's make our box plot. Now this is important this time. I got to press Y equals. I can't have that. That's got to go. Because my calculator probably won't like me asking it to graph that line and making a box plot. So I had to press Y equals, clear that. I'll press second, Y equals. Now I've already turned the plots off already, so I only got this one on, so I'll go ahead and go in there. Go down to type, and I'll keep pressing the right arrow key until this one, the one that looks like it's got outliers there, hit enter to select it. And X-list is in list 1, so I press second and 1 if it wasn't there. Frequency is always set to 1. And if I got outliers, pick which one you want. And just like I did for my scatter plot, what I'm going to do to get a nice viewing window, zoom and 9 for zoom stat. Aha, it's confirmed. We have an outlier. And now if I press trace, so that's the data value 95. And when it tells us to make a sketch above the number line, to make sure you've pressed the trace key, and then you can clearly see these values. So I say, oh, okay, so there's going to be one there at 30. The left whisker is going to go to 30. Left side of the box is going to be at 35.5, which is right about there. And the right side of the box is at 53 there. After I draw my box, and the line inside the box is going to be at 43, right around there. And the right whisker is going to go to just shy there of 70. And then you got this big gap here and just a point right there at 95. Okay. So that probably brings back memories of exam number 1. So the shape that is right skewed, as we see from the stem and leaf, confirmed outliers thanks to the box plot, 95. So what are we going to use to measure the center of this data? Well, our first choices are mean, and for the spread, standard deviation. But do we get our first choices if there's either skew or outliers? No, we do not. And we got both of them. Now remember, you can have one without the other. You can have a normal shape here and an outlier. And you could have a right skew, with no outliers. Okay. So the idea is don't, sometimes what I don't want to hear is someone says, oh, I have an outlier and that skewed the data. No, it didn't. The data skewed the data. A single data value isn't going to create a skew. The bulk of the data is what determines if it's skewed or not. They treat the word skew like it's a verb. Yeah, no, that didn't cause that to happen. It's describing the data. It's an adjective. So let's get on down here. So we're going to use the median. So let's press stat. Hey, let's get the descriptive statistics, which so you press stat, right arrow for calc, and 1 bar stats, like you did on exam 1. So we're not going to use the mean. We're going to scroll down. We need to use the median of 43. Why? Because we've got a skew and we got outliers. And those will distort the mean and will not do a good job of representing the typical data value. So we're going to use the mean. Now, median. Now, the median is not the first choice because it doesn't get maximum information from the data. It's just based on position in a sorted list. But because of that, it's resistant to the skew and outliers, and it's going to do a better job of representing the typical data value. And to measure the spread, we are not going to use the sample standard deviation. That would only be if it was the bell-shaped normal and there were no outliers. But that's not the case, so we're going to use the interquartile range. And there's the formula for it. I need to go down here, take the third quartile of 53, and subtract the first quartile of 35.5. And that's the length of the box in my box plot. So that's the range of the middle 50%. All right. So I've taken some time for this older stuff, stuff from exam 1. I don't want you to forget about that. Those should be the easy questions, and it'd be a shame for you to be missing those because you didn't review your exam 1. Because remember, when you got your exam 1 back, I also gave you the answer key. So you can, you can basically retake your first exam and then go to that answer key and see how you did. That'd be a good way to review. Oh, yes. Now, back in chapter 4, remember that tool, the residual plots? They allow you to verify that the conditions are met for the linear model. So it's asking now, does the particular residual plot you're looking at, is it violating a condition for a linear model? So if it's is not violating, that means it's showing exactly what we hope to see in a residual plot. But if it is violating, okay, what is the thing that it's doing that's violating the condition? All right. So hopefully you know that for residual plot, this is what you want to see. Just a hodgepodge of points. Now don't confuse this with a scatter plot, or it doesn't make any sense at all. The idea is you got a scatter plot like we were looking at earlier. Can't bring it back as I deleted the data. But if I tip that regression line over so it's horizontal, put it under a microscope, that's basically what we're doing here. And this means there's constant error variance, no discernible pattern. So we'll say no, it is not violating any of the conditions. The plot of residuals is random. But here, this is lacking the constant error variance. For here we have a whole bunch of variation than just a little. So that's lacking the homoscedasticity, if we want to use the fancy term. And then here we got discernible pattern. So here and here, the conditions are not met for the linear model. Hey, by the way, for those of you who are going on for a second term of statistics, the chapter 4, the linear regression, you're really going to be reviewing that. And of course, these residual plots. Because see, what they're going to do in the second term is they're going to build on this. And they're going to teach you how to do regression for nonlinear things. So like when you see a pattern in your residual plot, it's not the end of the world. That means you need to be using nonlinear regression. Oh, great. Well, that's not a problem. In fact, if you go over to Stat and Calc, look at all these different things that end in rate. Those are different nonlinear regressions. So you'll learn how to use those. So you'll probably be using a software package and not your calculator. And then it'll build on it some more. And they'll teach you in the next term what many refer to as the crowning glory of inferential statistics. And that is, instead of just using one X variable to help you predict Y, why not use multiple X variables? It's known as multiple regression. So that way, a single X variable doesn't have to do all the work. Each one of these multiple X variables can all be contributing a part. Let's suppose that one X variable has an R squared of like 30%. Normally, right now, you think that'd be worthless. Let's throw it away. But no, if you know multiple regression, you'll say, hold on to that one. Let's get some more like that. And you piece them together, and combining a bunch of these together, it's much easier to get X variables like that. And then you're able to predict Y. It's a much more easier model to put together if you're using multiple regression. And you'll learn how to do that. And you'll be super better at making predictions using data from the past. All right. Oh, and then let's not forget, now this is what we were talking about earlier. Remember back here, we said the probability plot showed the data was normal and the box plot showed there were no outliers. So these right here are the probability plots. Here's the box plots. So what does this probability plot tell you? Let me zoom in, make sure you can see this okay. So what does it mean when these points are outside these boundary lines? Don't call them outliers. I mean, they can't be outliers. Go look over. Do you have outliers here? No, if I had an outlier, it looks something like this down here. So this shows no outliers, so you can't call these outliers. So what does this tell me? This tells you the sample is skewed. So this says the sample is skewed with no outliers. Okay, well, if you got a skew, you're not getting your first choice now, are you? Because the idea here is we want to use t-interval or sample sizes less than 30. Well, if that's the case, you better have no skew, no outliers. Well, I don't have the outliers, but I got the skew, so no t-interval for me. And when they say, well, why not? Because the sample was skewed. Don't say it has outliers because that's incorrect. How about here? You say, well, they're all inside the boundary, so there's no skew. There's no outliers, so yes, no skew, no outliers. It's reasonable to believe that this small sample came from a normal population. How about this one? Well, there's no skew, but there's an outlier. All right, no t-interval for you. Why? Because there's an outlier. So you've done that before, but nice to refresh your memory a little. Okay, let's take a look at this one here. Let's scoot that over. Scoot this over here. I can probably move this out of the way for now. I'll bring it back if we need it. Let me press Stat, go over to Test. So the maximum width of each skull is measured from a random sample of 24 skulls for Egyptian males who lived around 1850 BC. The sample mean was 134.5 millimeters, and the sample standard deviation was 3.48 millimeters. Now, with this, find a 90% confidence interval for the average maximum width for all skulls of Egyptian males who lived around 1850 BC. All right, so what are you going to do? What statistical method? Function are you going to use on the calculator, or how are you going to pull this off? Well, first question, what are they asking for? A confidence interval. All righty, well then let's go down here. Look at our list of confidence intervals. Which one is it? Well, let's see now. What type of data is this? Well, we're measuring, okay, and so that means it's quantitative data. Okay, now how many samples was taken? Just one sample of 24. Hey, wait a minute, is that a small sample for quantitative data? It is, isn't it? Well, what do we need to know if the sample size is less 30? Well, they need to tell us the population is normal. Or they tell us that they did a probability plot that had no skew, or a box plot that had no outliers. Did they do any of that? They didn't. You know what this means? The conditions are not met. Oh, now you never leave a problem blank. The conditions are not met. But this is how I can check to see who is and is not checking conditions. Because look, you just can't willy-nilly use these statistical methods anywhere you darn well please. Because this is a first choice method, being able to go over here and use t-interval. Now, if the conditions are not met, which they aren't, you got to use a second choice method. I know you don't know any second choice methods. Well, you will if you take Math 244. I teach those second choice methods. All right. But at this point, you need to know that the first choice method, which is all you know, you can use it here. Now, you'll go ahead. You could say something like this. Now, if the population is normal, then this is what we would have done. We would use the t-interval, and then you go ahead, enter this data in, get that confidence, and interpret it. Now, how large of a sample is needed? Now, you don't have to check conditions for a sample size question, because we're asking how large the random sample needs to be. And of course, you're applying this to the huge population. But you see, your sample isn't going to just be large. It's going to be really, really large, so that the conditions will always be met for a sample size calculation. So which of these three formulas am I going to use? Remember, I know it's a sample size calculation because of those words right there. All right. Well, this is quantitative data, and only one of them is for quantitative data. And which one is that? The only one that has a standard deviation in it, like you see there. Oh, that's this one here. Now all you got to do is plug in the numbers. They're telling you what the margin of error E is, and they're telling you what the standard deviation is, and you're going to look up that critical value right here in this table. Let's see, 95%, so I'm going to put 1.9600 in for this Z critical value. And then, of course, there's a decimal part. You round up to the next whole number. Let's see now. Got another one here. A brewery has a filling machine that fills 12-ounce bottles of beer. It is known the amount of beer poured in by this filling machine follows a normal distribution with a mean of 12.15 ounces and a standard deviation of 0.04 ounces. Hey, you know what's different about this one and the other things we've seen? They just told me the shape, center, and spread of the entire population. So I know everything. They've told me everything. I don't have to use, I don't have to test to claim what the population mean is. I know what the population mean is. And I don't have to do a confidence interval for the population mean because I know what it is. I don't need to estimate it. So I don't need any inferential statistics here. So what I'm going to do is I'm going to go over here. Oh, first of all, let me just press second quit, hit clear. Move that down here and let me get my little worksheet over here and a fresh sheet of paper. Now let's jot down what we've been given here. Oh, let's scoot this off to the side. So I've been told everything about this population distribution. So I'm not going to be using, whoops, that's out of focus. Let's try this. There we go, much better. And so they're telling us that the shape of the population is normal. They told us that. And they're telling us what the population mean is, which is our center, population standard deviation. So this is 12.15 ounces and 0.04 ounces. Now, here's the type of questions I can answer with this. If it's a population distribution type question, they'll ask me, what's the probability of one randomly selected from this population? So that one randomly selected bottle from this brewery here, what's the probability it'll contain between this many and this many ounces? Something like that. Or they'll ask me what proportion of all of these bottles have less than, say, 12.2 ounces, something like that. So they're either asking me to find the probability of the proportion of all these bottles being in the interval, or they're asking me the probability of one randomly selected being in the interval. Those are normal CDF type questions. So that's when you go over here, you press second vars, and there's normal CDF, and then of course there's the inverse norm. So let's suppose they'll say, so what's the cutoff point for the top 20% of the bottles that contain the most ounces? So they're telling me what proportion, what area is in the right tail there, and I want to find that lower bound of the interval. And inverse norm will tell me that. So you did work like this on exam 2, as you recall. But another type of question they can ask me is a sampling distribution question. So instead of asking about the probability one randomly selected being an interval, they could ask, what's the probability? So you're not going to randomly select one, you're going to randomly select more than one. Oh, right there, that tells you it's a sampling distribution problem because you took a sample. Or say you took a random sample of 20. You might say, wait a minute, 20, that's a small sample. That's less than 30. I say, don't worry about it. Our population's normal. So our sampling distribution is always normal. Oh yeah, that's right. So I could find the probability of the sample mean from a random sample being in a given interval. And so let's see what type of question they're asking. Is it a population distribution or a sampling distribution? They said if 25 bottles are randomly selected, well, there's your answer right there. That's not one randomly selected. That is a sampling distribution. So what do we know about the distribution of all the possible sample means we could ever possibly get by repeated sampling for that sample mean. Well, what do we know about its shape? Its shape is normal. And there's two ways this can happen. Either our sample size is at least 30, well, that's not the case here, or we're sampling from a normal population. So let's state this very clearly. Because we are sampling from a normal population. That's a lot more clear than someone who says, oh, it's normal because they told me it was normal. Well, what's it? You're being vague and misleading. I couldn't trust you to teach this to someone else if you just say it and people don't know which it you are referring to. Now, let's see the center. What? Whoops, let me spell that correctly. Center. That's all those sample means are going to cluster around the population. And we know what that is. It's 12.15. But how closely will they cluster? Now that's the standard error, our spread. So how closely the sample means cluster is given by this. You say, but what if I can't remember that little formula? You don't have to, just recognize, see, there it is on the formula sheet. Now this is the center for all the sample means. This is the spread for all the sample means. And hey, we know what this is. The spread of the population we're sampling from is 0.04. And we're going to divide by the sample size. And let's see now, I forgot what my sample size is already. I know it's less than 30, 25. You know what we should do? Let's see how small that is and reflect upon that. Because that's a really important concept. So those of you going on for a second term of stats, this is one of the things they'll do early in the term to see if you remember how to work with a sampling distribution to make sure you don't confuse this with a population distribution. That's their big concern. And if you are getting these confused with each other, that doesn't reflect very well on me now, does it? They'll say, who was your statistics instructor? That they didn't get clear to you the difference between those two. All right, so I'm gonna press second quit. And let's do 0.04, divide that by the square root of 25. Now, what is that? If something looks like a percentage, can you just willy-nilly turn it into a percentage? I sure hope not. That's 0.008, and that is a measurement. Ounce is a 0.008 of an ounce. So that's a pretty small measurement, but that's typically how far off your sample mean is going to be in its estimate of the population mean. You're going, really? That's pretty close. Those sample means are clustered pretty close around that population. Yes, they are. So when you do this, it really helps you understand or remind you, hopefully you've already reached the understanding part earlier in the term, that the sample means really do cluster very closely around the population. And the bigger the sample size is, the closer they cluster around it. And that's why a sample mean does such a good job of estimating the population. Okay, well, if I know the shape, center, and spread of all the sample means, then and only then can I calculate the probability of the sample mean. Oh, and also let's do this. Let's make ourselves a little sketch. Because our brains really like it if we give it a picture. It can just grasp the concept so much better. Now, when you do this, let's put our tick. Now, how many tick marks go in here that pretty much cover everything? 1, 2, 3. So I don't want to see any more or less than 3. Because if I do, then I know that you're missing some very important concepts, like the empirical rule. Now I'm going to put an X bar here since it's the distribution of, whoops, sorry, I didn't realize that was all tilted. all the sample means. What's in the center? The 12.15. And each of these tick marks is only 0.008. So where in the world is the 12.17 on here? Well, it's to the right. How far to the right? You know what the easiest way to find out where that locates? Turn it into a z-score. So take your 12.17, see how far it deviates from your center, which is 12.15. Then divide it by the spread, which is the 0.008. So let's calculate that, and that z-score will make it really easy to locate where it lands there. So left parenthesis, 12.17, subtract 12.15, and divide that by 0.008, and that's the z-score, 2.5. Now, so that means that this 12.17 ounces they're asking me about, they want to know more than that. So this is the lower bound for the interval is 2.5. 1, 2, there's 2.5 right there. So this makes it really easy to see where my 12.17 landed. So they want me to find the probability of landing there. Now, which way do I shade, to the left or to the right? Well, that depends what they asked for. If they said less than, I'd be shading to the left. They said more than, so I shade to the right. See that tiny little area? That's a picture of my answer. That area is what they're asking for, because that area is the probability of getting a sample mean of 12.17 or higher. Okay, so let's put that into notation. Oh, in fact, I can use my sketch to help me with this. So notice that my sample means are to the right of this. I'll put this to the right. On the number line, wherever's farther to the right is bigger. So there's the probability inequality notation. Now maybe you'll say, oh, no, Larry, I always like to write it like this. Okay, you can write it any way you want. Just make sure that the sample mean gets the big N. And of course, this is a job for normal CDF, because it'll take the interval. So my sketch is telling me now this is the lower bound. And anything way off to the right that's really big, I'll do one E99. Now make sure that you don't mess up on your interval. Making the sketch a good one will keep you from doing that. So you, as a general rule, if someone goes the wrong way, goes here to the left, usually they didn't make a sketch and they got messed up here and went the wrong way and got the wrong answer. Now let's put in our center. Well, that's right here, 12.15. And the spread, that's the 0.008. But what if I put in the 0.04 in there? Well, that's just telling the world you know what a sampling distribution is. Because if you put 0.04, you're doing a population distribution problem. Now, this right here is the big distinction between the two. This uses the standard error. If I was doing one of these, I'd be using the standard deviation. So very, very important to make that distinction. Well, here you've done all the work. All you got to do is punch it in now. So let's do that. So I'll press second bars 2, 12.17, comma. Now you don't have to do one E99 as long as it's something really big. 100 would definitely be far enough to the right. But I'll show off and do to get the E, I did the second key, the comma key, 99. And then my center is the 12.15. And then my standard error, the 0.008. Whoops, I got to get another 0 in there. I better double check myself. There's my lower bound, something big, lower bound, something big for the upper bound, 12.15.008. Looks good. Now, before I hit enter, I can see that, well, I know from here that's 2.5%. So this is going to be pretty small, definitely less than 2.5%. Let's see what we get. Yep, that's pretty small. And that seems reasonable because, that is a very small area. So my answer is 0.0062. That's what it looks like in decimal if I want to write it as a percentage. So that's less than 1%. That's just a fraction of a percent. So there's a 0.62% probability of getting a sample mean greater than 12.17. Now, interpreting this as the proportion of all the possible sample means you could get, this is the proportion of all the sample means that are going to be greater than 12.17. And yes, that would be an unusual event because that is much less than 5%. All right, so hopefully that's a nice little assortment of problems we worked on. And I'll make sure that this will be available to you after I get this all uploaded, that you'll be able to go to external links, click on recordings of live lectures. Now remember these, if you want to review anything, if you've got any problem areas as you've been reviewing for this, I always state what was covered on that lecture so you can go to that one and get some more help seeing those problems worked out. And so certainly by tomorrow morning or by late tonight, you should see lecture number 7 here, review for the final. And when you click on files from the live lecture, you should see the lecture 7 docs here, and you'll be able to get a copy of the documents we were looking at. Alrighty, well, I'll see you next Tuesday when you're taking the final.